Stokes' theorem says if capital S is a simply connected 2D surface, and this time I actually do mean simply connected, and the surface is in 3D space, so it doesn't have to be a flat surface like we were talking about for Green's theorem. In Green's theorem, we were just talking about surfaces or regions in the 2D plane that had to live inside the xy plane. This does not have to live inside the xy plane. This can be any surface in 3D space. But what I mean by bounded by the path boundary of S, what I mean is that, let's say you've got some crazy old surface living in 3D space. Gosh, this is hard to say. Imagine you have a blanket, right? You can deform the blanket and it can be any sort of shape you want, but there's still like an edge to the blanket. You know what I mean? That edge of the blanket, that's what I mean by the boundary of S. I mean like sort of the edge of the blanket. Okay, so what Stokes' theorem says is if you take a path integral around the closed curve that makes up that boundary, then that path integral is equal to the surface integral over the whole surface of the curl of a vector field capital F. So I should say capital F is a vector field. Okay, so let's see if I have any examples where this could be useful. It says use Stokes' theorem to calculate the following surface integral over the vector field F. And so I've got this surface, and I didn't write it out, but if I'm doing a surface integral over the vector field, I'm saying take this surface integral over capital F. And Stokes' theorem tells me that this is actually equal to, well, hold on, no it doesn't. What Stokes' theorem says is this. It had to be the curl, right? Not just the whole vector field. So this is what Stokes' theorem says. If I say capital G is a vector field, then the path integral around the boundary of the vector field is equal to the surface integral of the curl of that vector field. Okay? I'm just checking, make sure I memorized that right. But yeah, the surface integral is actually over the curl, not over the vector field itself. Okay? So it might not be immediately obvious how we could actually use Stokes' theorem here, because what my problem is saying, what this example is saying is, let's take a surface integral over a vector field F, and I'm not given the curl of this vector field, I'm just given the vector field, right? I'm asked, calculate the surface integral of F. So step number one, when you're solving this problem, is going to be this. Find a vector field G such that the curl of G is equal to F. And that way, the surface integral of F would be equal to the surface integral of the curl of G, and that I can use Stokes' theorem and take the path integral around the boundary of that surface and get this. So step number one is actually kind of tricky. Just giving you a warning. If I give you a question like this on an exam, this is actually a little bit difficult to do. We're trying to find a vector field capital G such that the curl of that vector field be equal to F, and at least for this problem, F is a pretty simple vector field. So my vector field F is y0, 0. So let me just say capital G is going to be a 3D vector field, and we'll call these entries G1, G2, G3. Okay. So the curl of G is going to also be a 3D vector field, but the curl of G is going to be the partial of G3 with respect to y. And sorry, I memorized this all out of order. So that's with respect to x, and then 2 with respect to x, I think. And then this is minus the partial of G2 with respect to z minus the partial of G3, with respect to z, and then minus the partial of G1 with respect to y. I'm almost certain I made a mistake.
Isn't it G2 partial y minus G3 partial, what, G2 partial z and then G2 partial y on the first one?
Let's check my work. Let's actually do this the proper way that I should have done to begin with. So, curl of G. That is the determinant of this 3x3 matrix looking thing. But this is the partial with respect to x. This is the partial with respect to y. And this is the partial with respect to z. Okay. Then this is G1, G2, and G3. And so this again is a 3D vector where the first entry is going to be partial of G3 with respect to y minus the partial of G2 with respect to z. And then the second entry is going to be minus j, right? So minus j, and then the partial of G3 with respect to x. And then normally I would subtract the partial of G1 with respect to z, but this is minus j, and so I say plus the partial of G1 with respect to z. And then the last entry is going to be the partial of G2 with respect to x minus the partial of G1 with respect to y. Okay, so double checking my work to see if we did everything right, see what we did wrong. The first entry is good, right? The second entry is also, it's almost good, but that should be an x and not a z. What about, oh, I also messed that up. That should be a z and not an x. Ooh. Okay. And then the third entry is actually right. So I'm glad I checked my work. I tried to skip a step, but I was wrong. And so I'm glad we sat there and checked it. And there we go. So now we're good. Now we know what the curl of G should look like, right? So there's actually a lot more ways than one to make this happen. What I mean is there's actually a lot of different vector fields G such that the curl of G is y0, 0, okay? There's an easiest way to do it, though. There's one way that's going to be a lot easier than the others. And what I'm thinking about is this very first partial derivative that says the partial of G3 with respect to y. I want to set that equal to y. And so that means if I look at the third entry in my G vector field, I want that entry to be y squared over 2. That way the partial derivative of the third entry with respect to y is going to give me just y. And then we can double check, but if you take the curl of this vector, that should give you y0, 0, right? Because this partial with respect to y is y minus 0, and then in the second entry we have 0 minus 0, and then the third entry we have 0 minus 0. Okay? So this G is a vector field that checks out. This is exactly the kind of vector field we're looking for. Like I said, there's lots of ways to do this. This is not the only vector field G that works. It is the simplest and the easiest one that works, but it's not the only one. This is kind of a hard problem in that way. Okay, but if step number 1 is done and we found what capital G is, now again, if I want to calculate this surface integral, all I have to do is calculate this path integral. And if I think about this surface is the top half of a sphere. And the sphere is going to be centered at the origin, and it's going to have radius what? Yeah. So the surface capital S, that's the top half of a sphere of radius 3 centered at the origin. So if I then asked you about, what is the boundary of S, what is that? If my blanket is a top half of a sphere, what does the edge of the blanket trace? A circle. It's a circle with radius 3 that lives in the xy plane centered at the origin, right? Okay. So partial S, I could write that as a parametric curve and write it 3 cosine t, 3 sine t, 0. That's a parametric curve for a circle of radius 3 in the xy plane centered at the origin. And I just want to really drive this point home, so I'm going to graph it, right? But what we had was z equals square root of 9 minus x squared minus y squared. That was what I told you my surface S was. And so, again, whenever I talk about the boundary of a surface, what I mean is where this surface ends, which is in the xy plane, that's what I mean. I mean that circular path that catches the edge of your surface. Okay? Cool. So now I can take this integral over my vector field G around that path, and we'll be good. So a path integral is just going to be a single integral, and my parameter t is going to go from 0 to 2 pi because it's tracing the circle. I have to think about how to do a path integral over a parametric curve again over a vector field. So this is y squared over 2, right, for my G vector field. And then we do the dot product, not the dot product with the parametric curve itself, but with the derivative. Remember, you take the derivative of the parametric curve. So the derivative of 3 cosine t is going to be negative 3 sine t. And then the derivative of 3 sine t is going to be 3 cosine t. Honestly, those don't matter, because you see you're about to do the dot product with the zeros. And then, of course, the z coordinate was 0 for the whole parametric curve. And then we take the integral with respect to t. But clearly my integrand is 0. And so this is 0.
What time is it?
We leave
Hmm?
at 3. Yeah. And I give her a heads up that to reschedule yours at 1. Yeah. I know that you rescheduled after that, yeah.
Huh.
Because I didn't see you in the morning.
It's true.
I haven't taken it yet.
So if you had a question that said, verify Stokes' theorem, what you could then do is you could also take the surface integral of the vector field y0, 0 over this whole surface. You would just have to find a way to parameterize it. That's not too difficult. It's definitely more difficult than this, though. So here we go. Use Stokes' theorem to calculate the following surface integral over the vector field f. So this time my vector field is a little bit trickier, and my surface is a little bit trickier, but the problem is still the same problem, right? Probably what you can see here is if I wanted to take the surface integral over that surface capital S in vector field F, this would be a huge pain in your butt. Like, that surface is going to be really difficult to parameterize, and that integral is just going to be a nightmare. Especially because with surface integrals, you got to take the partial derivatives with respect to your parameters, and then you got to take the cross product, and then you've got to do the dot product, and then it's just a whole thing. So the way this becomes easier is if we were to find a vector field G such that the curl of G is equal to F, well then this is the surface integral over the curl of G, and Stokes' theorem then says this is the same thing as the path integral around the boundary of my surface of G. Right. Okay. So step number 1 is going to be a little bit trickier than it was before, because, let's see, I need the curl of G to be equal to F, and this time F is y z squared 0. Okay. The curl of G, if I say that G is equal to G1, G2, that's not a 6, that's a G. G2, G3. Then the curl, help me out because we just wrote this out and I don't want to write it again. No, it's the partial of G3 with respect to y. And then it's the partial of G1 with respect to z. And then the partial of G2 with respect to x. Okay, then we do the minuses. And then we have the partial of G2 with respect to z. And then we've got the partial of G3 with respect to x. And then the partial of G1 with respect to y. Okay. It's easier to memorize than you think. It looks really difficult to memorize, but there's a few things you can pick up on that make this easier. Because number 1, I associate the first entry with G1 and with X. But notice in the first entry, there's never any G1s or X's, okay? I associate the second entry with G2 and with Y, but in the second entry, there's no G2s and there's no Ys. And then the third entry, you normally think about G3 and you think about Z, but there's no Zs and there's no G3s. So think about that rule, that the things you normally associate with the first, second, and third entry, those are excluded. You can't pick those. Then I just have to memorize that the first thing is G3. And then the other sort of exclusionary rule is that I never take the partial of G3 with respect to Z. It never happens. You never match up partial of G3 with respect to Z. You only take the partial with respect to Y and X. The other thing is G2, you never take the partial with respect to Y. You only take the partial with respect to X and Z. And with G1, you never take the partial with respect to X. You only take the partial with respect to Y and Z. And so if you keep those exclusion rules in mind, then you can actually reason out the rest of it, right? If I already picked G3, then I can't pick G1, so I have to pick G2. And I don't know. If I'm doing this first entry, I know the partial can't be with respect to X because it's in the first entry. This is also the partial of G3, so it can't be with respect to Z, so it has to be with respect to Y. And so if you really spend 10 minutes trying to memorize this, you could definitely memorize it. And then, if you mess up like I do, you can still check your work like we did a second ago. You can still check your work using a normal way of taking the curl. But anyways, it's easier than it looks, but you still might. If it's a high stakes exam, you still might actually check your work by taking the curl. Do that on like the front page of your exam, and then you can use it later. But anyways, this is what we want to happen. We want the curl of g to be equal to y z squared and 0, but we don't know what g is. So what we'll have to do is we'll just have to start taking a guess for the entries of g. Just take a wild guess, and then we check and make sure it works. And if it doesn't work, then we kind of revise our guess. So I want the first entry to be a y, and I'm looking at partial of the third entry with respect to y. And so let's try to make the third entry y squared over 2. So far, so good. Now I want the second entry to be z squared, and the second entry should have a partial of the first entry with respect to z. And so maybe the first entry could be z cubed over 3. If we want to check our work, we could take the curl of that g vector that I just came up with, right? So let's pretend to take the curl of it. The partial of the third entry with respect to y would be y, perfect. The partial of the second entry with respect to z is 0, so we have y minus 0, and it works. Okay. The partial of the first entry with respect to z would be z squared, that's good so far, minus the partial of the third entry with respect to x, that's 0, so z squared minus 0, and it works. The partial of the second with respect to x is 0, the partial of the first with respect to y is 0, and that works too. So you guess and you check. I said this earlier, but there's infinitely many ways to choose a capital G such that the curl of G is y z squared 0. I normally try to make that G vector as simple as possible. Okay? There's lots of different ways you can do it, but this is the easiest way, I think.
So basically, like, you just focus on the first part of the difference,
Mm-hmm.
like the G3 and then G1, G2.
Yeah. Yeah, and this problem, I'm going to take a little aside here because I think it's neat, but this problem of finding a vector g such that the curl of g is equal to a vector f is not always solvable for every vector f. It's not always solvable for every vector field f. The reason is because for any vector field with continuous second partial derivatives, you know that the divergence of the curl of the vector field has to be what? 0, yeah. And so since we are talking about making f the curl of g, so let me say the divergence of the curl of the vector field g, that has to be 0. Well, we just said that f is going to be the curl of g, and so if we want this to work, then the divergence of f has to be 0. So if you're talking about some vector field where the divergence of that vector field is not 0, then it turns out you can't do this Stokes theorem trick to it. The Stokes theorem isn't going to be useful because you won't be able to find a vector field g such that f is the curl of g, because then it wouldn't satisfy this equation. Okay, so I think that's neat, but in this case, my vector field f, if you take the divergence is 0, so it still works. Anyways, we found what g should be, and we decided that the surface integral over f is going to be the same as the path integral around the boundary of the surface of g, And now we just need to think about what should the boundary of the surface be, how do we write that boundary as a parametric curve, and then we can do the path integral over the parametric curve over the vector field G to get our answer. So here is my surface. It looks really crazy, but one thing about my surface is that there's a square root. And so as long as we're talking about real numbers here, the square root only works if the radicand is positive. And so where the radicand is negative, our surface won't be defined. And when the radicand is 0, that would then represent some sort of abrupt boundary of my surface. And so maybe what we should do is we should set the radicand equal to 0, since what we're doing here right now is we're looking for what is the boundary of the surface. Let's set the radicand equal to 0. So we might write something like 9 minus x squared plus y squared squared plus 8 times x squared plus y squared is equal to 0. We might write that as we're looking for our boundary. What is x squared plus y squared, though? Yeah, that's r squared. So I don't really have to think about the x's and the y's separately, because every single time those appear, they appear as x squared plus y squared. So we can simplify that equation by switching to polar coordinates, and I get 9 minus r to the 4th plus 8r squared equals 0. So let me write that again as r to the 4th minus 8r squared minus 9 equals 0. And I'm trying to think, does that factor? Yeah, that factors. Okay, so that factors as what? R squared minus 9 and r squared plus 1. So r squared plus 1, that's only going to have the roots I and negative I. So we're only talking about real number calculus right now, so we don't have to worry about that. This has roots at r equals 3 and positive 3, negative 3. But we're talking about r as the distance from the origin, and so negative numbers as a distance from the origin, that doesn't make sense. So we can just think about r equals positive 3 as the solution here. And so that means our boundary of the surface is when the radicand equals 0. When the radicand equals 0, then my coordinate z is equal to 0. So we're talking about the xy plane. And we're talking about the set in the xy plane where r is equal to 3. So again, we're talking about a circle with radius 3 as being the boundary of this surface. We actually have the same boundary that we had in the last problem. It's just a circle with radius 3. So in the last example we worked, we had this. We had a nice half sphere, and it was easy to recognize that that boundary of that sphere was the circle of radius 3 in the xy plane. But now if we type in the really crazy equation that we got for this surface, the square root of 9 minus, it was x squared plus y squared squared plus 8x squared plus y squared. Just want to see what it looks like. Okay, so this is, again, the surface that we're talking about doing a surface integral over. But the nice, neat thing for us is that the boundary of that surface is just that circle in the plane again. That makes sense? So again, this is where we need to use Stokes' theorem, because I'm not about to do that surface integral over that crazy surface. I'm not going to worry about that. But the path integral of g is actually going to be a lot easier. We already know what g is. the boundary of G is a parametric curve that I can parameterize as 3 cosine t, 3 sine t, 0. And then I'm just making room over here. The path integral we want to take is going to be the single integral from 0 to 2 pi of the dot product between G, which is z cubed over 3, 0 y squared over 2, and not the curve, right, but the derivative of the curve. So that's going to be negative 3 sine t, 3 cosine t, 0 dt. So when I take the dot product, the 0 terms don't matter, and what I'm left with is 3 cancels 3, and then I end up with negative integral from 0 to 2 pi of z cube sine of t dt. But what is z in my parametric curve? Z is just 0. So actually both my examples today ended up being zeros, so that's not very exciting.
How can we interpret the 0 as an interpretation of the 0?
Well, so what we were initially trying to find is we were trying to find a surface integral over this vector field f, right? And we were only ended up solving that path integral because Stokes' theorem says that that was going to be possible.